Alright, everybody, howdy, and welcome to the first out of cycle official sort of tutorial since I started up the Patreon for NES Game Maker, where instead of talking about NES games specifically, we talk about messing around with code in general and different code applications. So I was going to try and make a sort of slick looking PowerPoint presentation and stuff for this, but like Friendly Cosmonaut, but then I decided, that's not really my style. So instead, I made a really nice presentation for you all that I could talk with you about. So what are we going to be talking about here? We are going to be talking about pseudo-random number generators. So let's get cracking on that. So I have over here, down over in the notes, a list of sources. This is a bunch of useful information that is where I got all my information from and all this stuff. So this tutorial or this bit of information I've set up here will show you how to set up a couple of pseudo-random number generators. So we have over here our different ones. You can ignore this. That's just where I built all the code originally, and then I kind of made it into a fancier stuff after that. So we have the built-in pRNG, and that uses some code that nobody really knows what exactly it is. So, but it's a fairly good random number generator, and you should use it as much as you can for anything where you need random numbers. But sometimes you have specific needs, and this is kind of the main use case for all these pRNGs that I'm talking about here. So you might have a game where you have a player who's flipping a coin, and because of the way the pRNG is set up, in 2 more tosses he will get the number that he wants, right? But then they save the game and quit, and then they come back to the game later on. Now, if you were using the built-in pRNG doesn't keep the state of the random number generator, even though it keeps the seed. So, or it doesn't even keep the seed. If you use randomize, it would use something different. So that 2 more flips to reach his number will now suddenly be who knows how many more flips. But if you use your own ruled pRNG, you can keep the state of your pRNG, so when he reloads the game, it will still be 2 flips away before he gets to his number. So that's the main use case for these pRNGs. As far as I can tell, there might be something more if you can come up with it. I hope you can. So please do so. Let me know if you do. Anyways, so let's see. We have the built-in pRNGs, so we could start off with that. Let me get you familiarized with all of these objects here. So we have the seed, the probability. So in our step events here, ignore this for a moment, we do a convergence test to see how fast it reaches our probability. So our probability here is 0.5 or 50%. So we run this code through a loop here to see how fast it takes to get to that probability, basically. So you can change this to 0.25 or whatever. It doesn't really matter. And the pRNG number is just whatever number is being rolled. In this case, we're using random 1. Then we have black squares and white squares, which will be useful in a bit. Temps, color me, success, attempts, and success rate. So we start off by setting the seed for our RNG for the built-in RNG to whatever we have here as a seed. Technically, we could also do randomize, which just generates a random number to use for this value here. Then after that, just a little stuff to resize the engine for your screen there, and setting up the font. So come over here. If we press space, we'll generate a new seed and reset our attempts and success rate so that we can start converging again with the new seed. We have this toggle here, so if you press enter, it turns on color for the demo. And of course, if you press escape, it kills the game. And then if you press shift, it moves on to the next algorithm. So from the built-in pRNG, we go to the linear congregational generator, and so on and so forth. Over here in the draw event, so the code in all these is pretty much identical. There's just a little bit of variation depending on how the specific pRNG is set up. But again, we set our black squares and white squares to 0. Then throughout the height and width of the room, we generate a random number. And if it's greater than our probability, we set it to white. Otherwise, we set it to black. And we count up our squares as well. And if you have color set up, instead of being white, it will be colors. And we also have a draw GUI, but you can probably ignore that. The main meat of the code that you're really worried about is the stuff that's going on here. As random is built-in function, there really isn't anything that you can learn about it. So we'll move on to the next one. But first, let's show it off here. So you can see we're generating a random static pattern across the screen here. There's no visible pattern, so it's just a random noise for the most part. You can turn it into color if you feel like it too. So that's looking pretty good. So we have over here this linear congregational generator. So if you're interested, there's a lot of history on how pRNGs were created. So starting off with von Neumann at the Manhattan Project, setting up the nuclear bomb. He came up with what was known as the middle squares method, and we actually have a middle squares whale method, which is a modification of the original middle squares method to make it a exceptionally fast and useful generator for this day and age. Then we have here the object. We have the linear congregational generator, which was developed in the 50s, and is a very powerful and useful generator. It's very fast, but it suffers from a major flaw. Mainly, it's in the title. It is linear, meaning the inputs. So since it's linear, you can never have two numbers that are the same. If you end up generating the same number twice, you get caught in a loop, and that creates a pattern. And actually, that's what's known as the period of the random number generator. So in this case, our period is 2 to the 32. So we can generate up to 2 to the 32 random numbers. That's useful for most applications. Well, 2 to the 32 is actually pretty low, but it still is good enough, especially for our floating point numbers. So anyways, so as you can see, the code is for the most part the same, but we have this modulus, a multiplier, and an increment. And these values were the ones that were used by Borland Delphi. A lot of linear congregational generators were used for many, many years, and most and are in some cases, I think they might still be used, but I don't have any actual confirmation of that. But it's used since it's so fast. It's really useful for generating random numbers. But as I said, if you have two numbers that are generated that are the same, then you get stuck in a loop, and that would be the period of the generator. But more importantly, because it's linear, if you know the output, then you can actually work backwards with some math, and you can figure out the inputs, which then lets you reverse engineer the random number generator so you can practically generate any number you want at that point, because you know what the state of the generator is and what the next number it's going to generate is and whatnot. So that's actually very bad if you want to keep a secret what you're going to be generating next. So we use a script here, LCG random float, which runs the code that we are going to be using. So we do with object linear congregational generator, and seed equals multiplier times seed plus increment. This is a formula that you can find on the Wikipedia page for this. There you go. And then you return the value that you generate divided by the modulus, aka the period, because that's the maximum number you can generate, 2 to the 32, and that gives us a floating point number. I've also included, so in our LCG folder here, we have LCG random int, which is the same thing except you don't divide by the modulus, and we have the float, but we also have Boolean, which takes LCG random float, and if you're greater than the argument, so it'll give you a Boolean based on the percent, so it'll give you true or false depending on if you're greater or less than the argument. And then we have int range, which is the so it'll give you values within the int range only. So, and also float range, which is the same thing except within the float range. These are all analogs of the built-in functions that are in the built-in pRNG for GameMaker. But since I implemented them here so that you know how they work, so you can use them yourself if you need to. Alright, let's close all that stuff. And of course, draw event, same thing, just change this over to LCG random float there. And let's give it a test. So here we go, linear congregational generator. It looks pretty much the same, just a bunch of static, and it's actually moving about the same speed almost, you'd think. But it's actually significantly slower than the built-in pRNG. But as you can tell here, it is moving at a pretty good clip. At least you can see it when you're running it on your own computer. But then we pop open the middle squares method. And this is where I started getting fancy, I hope. This is also where I ended up spending up the most of my time, because at this point, the LCG, it's fairly easy, and probably the reason why you got to implement it was used so much is because you can implement it anywhere, and I don't have to worry about whether or not that's I don't have to worry about a cap on the numbers or anything. So, but with these next two engines, we actually have a problem, because they are supposed to be implemented using unsigned 64-bit integers, and unfortunately GameMaker language does not allow you to use unsigned 64-bit integers. Everything is signed, so that breaks a lot of the implementation. So I spent a lot of time trying to find ways to get around that before I decided, okay, there is no way around it, so we got to just rewrite everything to be using 32 bits instead of 64 bits, which isn't as desirable as you want. So with the middle squares method, we have, again, 3 different variables, kind of like the linear congregational generator. But we also have the ability to, with the middle squares method, this is actually, according to the white paper that I read this off of, if you were able to implement this properly at bit level, It is actually one of the fastest random number generators available, but unfortunately, since it is not implemented in such a way, then it ends up being not as fast. And part of the reason why it's not as fast is because it is not a linear engine, so somebody can't copy the can't decipher the way the engine works based on, they can't decipher the seed or the way the engine works based on the output, which is actually very important, especially if you want to do some sort of cryptographically secure thing, like making a 32-bit key for your game, for like, I don't know, you could possibly use it for key implementation for making sure the copies are valid or something. I have no idea. Anyways, so we have the middle squares method. We have, actually here I'm using hex numbers because they're more convenient to use when I'm working with bits. So in this case, it says that the seed needs to be an odd 32-bit number with half 0 and half 1 bits. So what does that mean? That means you have to have all of these need to be different, and the last digit needs to be odd. So, and that'll get it working on this one. It's also kind of, in general, it's seed sensitive. So if you get a bad seed, you end up with some bad results. In this case, actually, I have these set as 0 and 0 here. You should set these to some random number as well when you implement it yourself to prevent, because if you have it at 0 and 0, it makes it so that it takes several runs of the engine before you start getting actually random numbers. So, anyways, when we press space here, we reset the X and W to zeros again, and attempts and success back to 0. And we set our seed to be a random power 232 in 64. And I should probably change that to just random power 232. But I think I've set the N64 to make sure that it so that actually I don't think it makes it any difference here. I was probably, when I was testing the implementation to see how that would work. Anyways, so this would go to the Zorshift engine on the next attempt as well. And of course, do our test, MSWS, random float. Got all of our code over here. Over in the draw event, again, you just have MSWS random float. All right, on to our important stuff right here. So we have a bit of code here. We have x underscore is equal to, so when we do the middle squares, we have to square our number first, then add our seed number to W, then our W to our X, and then we do a shift of the bits in a circular fashion, and that generates a new number. And finally, we take that number and we limit it to the 32-bit range by doing and 0xFFFF, and that limits it to 32 bits because remember we need unsigned 32 bits and for our numbers in this system for it to work properly. Then we divide it by power 32, which is this right here. That gives us a value. Let's see. So you can see middle squares, it again is working really well. I press space a couple times. Let's see what happens with our seed. Looks like we're doing all right as far as the seed is concerned. We're not hitting anything that would be bad for the seed. And it's working fairly well as a 32-bit generator. By the way, this is a 65536. That's 2 to the 16 numbers that are being generated right here. So that's about half our periods. So last but not least, we would have the Zorshift. Now this is actually the most complicated, and this is probably the one I would suggest you end up using if you're going to be implementing these things into your games. I suggest either the middle squares or the Zorshift. The middle squares is easier to use and easier to implement, but the Zorshift gives you more numbers instead of 2 to the 32. With Zorshift, you actually get 2 to the 128. Because the Zorshift, instead of just being a simple seed system, it actually includes a pRNG state system. So you have 1, 2, 3, 4 states. So you can hold up to 4 numbers in memory, so to say, at a time. So those all add up to 2 to the 128 bits of randomness instead of 2 to the 32. So Zorshift, we have our random float, which we're going to be generating here. We also have Zorshift generates seed. This uses a algorithm that will generate some random numbers, and it's kind of overkill. Me haven't even implemented that. That's a completely another RNG. So that's split mix 32 that I implemented there. And I completely didn't need to do that at all because you could have just used the built-in pRNG to generate the seed states for this just fine. The reason why you do that is because apparently you need to generate the seed states with some other engine beforehand, or just by selecting them from random whatever. And this engine is actually really sensitive to what seed you choose for it. So, the states that you choose for it, I guess I should say, rather than the seed. Though the seed may be part of it as well. If you, when you're testing this out, you'll notice this is actually very slow compared to the other pRNGs, for one thing, because it's much more powerful. But also, if you get a bad seed, like right there, you'll end up with a low period, and you'll start having a broken system at that point. So when you implement it, just choose random seeds and for your state until you get one that fits into the period, and you'll be just fine at that point. And this one uses a bunch of really fancy math here, but overall it kind of works like, well, what happens here is, ignoring this for the moment, we take our states and we Zorshift them against each other to generate new values. And this T is a value that we generate up here as well. And then we do a rotational shift down here. This is all math that I didn't work out, of course. Again, the origin of the math is in the notes here. I highly suggest you read the website. It's got a lot of interesting code in there. Then return the results, divide by the power of 32 again. And the reason why you can do 1 to the 28th is because instead of being able to only generate, as soon as you hit the same one number, you would end up into a loop. Since you have 4 different states, you can hit the same number multiple times. But if the state is different each time you hit the number, so you have 4 different states, that's like 16 different ways you could hit that same number. And they would all be different in each one of those cases. So you can hit the same number multiple times without going into a loop. Then, of course, we have the results. We're returning by sending rodal pRNG state 1 times 5, 7 times 9, and 0 FFFFF. So yeah, this is all code from their website. This is the Zorshift 128 star that I ended up using. I tried using the Zorshift 128 Plus to start off with, but the result would be flat, which was not desirable. And I tried the other engines as well, and they weren't as good as this one. This one gave the best results, at least when working with a game maker. If you had access to, if you were doing your game in Unity or something, since I believe you can use C and Unity for your programming, then you would be able to use the other engine just fine in that case. Anyway, so step, we do all this stuff again. In the draw, we do all this stuff again, and it's the same again. So we actually have one last pRNG here I wanted to show off. This is a Sobel sequence pRNG, and unlike the other engines where you would actually have a random value, the Sobel engine gives you a pattern. So we got here 0.5 is our target here, and we are getting a pattern of 0.5. And there's very, very, very little variance from this pattern. And this is actually really useful. And so I have set up here a little system. So we have enemy types are bat, snakes, unspeakable cosmic entity, and particularly evil snail. And we have a kill count. So we want to know how many times we've killed them. So we come over to our draw, and let's say we're killing the bat. Then we need to increase the amount of times we've killed the bat after we run the engine here. You could run it before if you want, but you'd have to take out the plus there if you're doing it that way. But I digress. So we have to keep count of how many times we've killed an enemy in this case, because it's important for keeping the track of our position in the pRNG. So if we want to, and again, we do 0.0005, so 1 in 500. So you can see we're getting 1 in 500 here, and with very, very little variance in our results. And why do we care about this? Because a lot of times, and this is especially useful with stuff that are the bigger and bigger the chances of you actually hitting it are. So if we have something that has a very low drop rate, we don't want the player to be frustrated because it took 2,000 attempts to drop their 1 in 1,000 item, right? So by using a pseudo random number generator, we actually managed to avoid that randomness that comes with true random numbers, or at least pseudo random numbers, because they are only a 1 in 1,000 chance. It doesn't necessarily mean that it'll be 1 in 1,000. It could be it could take, like I said, 2,000 attempts before you actually get your item of choice. But with this system, you actually get your item of choice after 0.5 drops. And actually, a lot of games are running this type of engine in the background. You can tell it because a lot of times the games will have a lot of statistics about how many of each enemy that you've dropped, that you've killed. And the way they're getting those statistics is because they're keeping track of it for their pseudo random number generator that they're using to make sure you get your drops after X amount of time instead of completely randomly. This would be more for really rare items, probably. For something that has like a 1 out of 4 drop, who cares about running a pseudo random number generator on it? What really matters is that 1 out of 1,000 chance drop that you want to have be 1 out of 1,000. So anyways, this entire project is available on my Dropbox. So download it if you want to have the opportunity to implement your own pseudo-random number generators. As you can see, they have very, well, like with the Zorshift, because we can maintain our state and we can save this data whenever we save our game. Therefore, we can keep our random number generation going in exactly the way that we want it to go. And same thing with this. We save all of our information about drop rates, and we can drop our items whenever we want them to drop. And the good information about them is because they're not linear, people can't reverse engineer them, and they're cryptographically secure. You could use these for generating, I don't know, some sort of private key for accessing your website or something. If your copy is legit, I don't know. You might be able to come up with some good reason to use this kind of stuff other than what I got here. Anyways, thank you everybody for joining me, and well, now that I've gotten this all taken care of, it's time for me to move on to working on that revamp of the tile collision system, so that we can finally get that set up to work properly with all of our tiles by default, and also just in general making it more robust. Part of the reason why I've been doing all this stuff because I've been trying to learn more about how to use bitwise math, since it's apparently faster than regular math. So I'm hoping I'll be able to implement some of this stuff into our tile collision systems to speed up our collision systems even more than they currently are. So anyways, until next time, good luck with your programming.